Okay. Let's get started.
Welcome everyone to the Identifier Locator Addressing ILA BOF. I'm Sumita Chakraborty, co-chairing with Joel Halpern, and responsible AD Suresh Krishnan, and IAB Shepherd is Eric Nordmark. We have Minute Taker, thank you, Machunduri, and Jabber Scribe is Evangelis. Thank you, and we have the online agenda, Jabaru, Mitico, Etherpad on this slide. And next is Note Well. So you are probably familiar with all the Note Well rules and notes. So Identifier Locator Addressing ILA BOF. So basically, this is a protocol to implement overlay, without encapsulation. So using ILA mapping in the IPv6 address, you can use the similar whatever you can achieve the encapsulation when transporting the packets between the nodes. It has some additional benefits, control plane and data plane separation, as well as anchor-free routing in many use cases. So that's the premise of this BOF, and the scope of today's session is mostly information exchange, and this is a non-working group forming BOF. So we want to make that clear. Lots of work has been done in this space in IETF. I don't want to name them separately because I might miss someone, some protocols, but basically separation of control and data planes, ID and locator separation and address mapping has been also worked out here. So today our purpose is not going to compare those solutions or not going to go into solutions in any way. So we will ask the crowd to just understand the problems, the issues that ILA addresses, and the use cases. So just for the informational purpose and then why it is needed, that's the purpose of today's BOF.
Yeah, it's discussion of the problems, the scoping, those aspects, and specifically not, well, you could use protocol foo or protocol bar. We're not debating that today.
Yeah, the agenda is simple. We will have Tom Herbert presenting problem statement, scope, and the issues. I believe he's also going to discuss the data center network use case during the same presentation. And then Kalyani Bogineni will be presenting on the 5G user mobility use case. And then we will do the Q&A. We request that during the presentations, due to the shortage of time, we would only accept the clarification questions. And then at the end of the presentation, we will have enough time for Q&A. So with that, we say that there are number of ILA-related drafts that has been discussed in various working groups, such as Interia and DMM, and maybe separately in side meetings. So with that, we should start today's presentation, and after that, we will ask we will have Q&A. So Tom, please. Yeah, that's right.
Okay, so I'll go ahead and,
Sorry, please.
my name's Tom Herbert. I'll be talking about kind of the background of ILA. This will be mostly the general aspects of it, and then we'll go into specific use cases with Kalyani. I would like to thank the chairs, AD, for organizing this. That's much appreciated.
I just don't know why. I've never had this issue. No. Okay. Hopefully it'll work. Okay.
Okay, so identifier locator addressing. I'll start with the goal. So the goal is to provide seamless mobility for multiple use cases using highly efficient identifier locator techniques. That's a pretty short statement that's actually packed with 4 different components: seamless mobility, multiple use cases, highly efficient, and identifier locator. So we'll look a little bit at those. The use cases, so we have multiple use cases. It's inherently mobile protocol, so anything to do with mobility, actual mobile networks, which is the first use case. And we also have use cases in data center virtualization, network virtualization. ILA was actually born from the point of view of network virtualization, in particular container virtualization, as a more efficient means of doing encapsulation. So you can also consider that as we move forward, there may be converged networks that have more than one of these kind of use cases inside the network. Hence, we have the possibility of converged use cases. So the problem statement. What we did here was we listed the problems and the applicable use cases. So this goes kind of from the general problems to more specific use case problems. So as I mentioned, encapsulation is expensive as a data plane protocol. And the way to think about it is when you're encapsulating an application that requires high performance, encapsulation basically becomes a tax on every packet. So there are certain circumstances, low latency, high performance use cases, where even that encapsulation becomes problematic. And it also contributes to bandwidth on the wire. So every byte that I'm putting into encapsulation is a byte taken away from MTU, for instance. There's a related issue, which we see a lot in IETF, which are tunneling considerations. So in the network, when encapsulation occurs, we consider that tunneling, and then several considerations kick in. For instance, what happens if your encapsulation exceeds the MTU at that point? Do you fragment? Do you not fragment? So there is an RFC on that. Just previously in TSV WG, they were talking about ECN and tunneling. So how do you deal with ECN and tunneling? DiffServ has an equivalent consideration. If you're doing UDP encapsulation, then you need to worry about UDP checksum. So the short story here is whenever encapsulation or tunneling occurs in the network, there are more considerations than just creating a new packet. Another one that's sort of general, and this is kind of well known in IETF also, identity is tied to location. So this goes back to the original definition of IPv4. When you have an IPv4 address, it exposes both identity of who you're talking with and also location of where they are. So this coupling makes it difficult, especially in mobility, to separate out those notions. So that's one of the things we're intending to fix. The next one, support for alternate protocols. This actually has to do with encapsulation. What we found is whenever we diverge, especially in the data center, from using plain UDP, plain TCP over the network and start using encapsulation or extension headers, inevitably some network device will not like that. And usually this is not breaking connectivity, but what it does is it reduces the number of optimizations. And that obviously gets us into the whole arena of vendors trying to support various encapsulations and an endless stream of that. So anytime we try to come up with a new encapsulation or a new scheme, we do consider the effects of existing network devices in the middle of the network. Privacy and addressing. So this I touched a little bit on in area discussion. So this goes more into what kind of addresses are we exposing to the internet. And it's not so much that this is a problem to be solved in identifier locator addressing. It's more, can identifier locator addressing kind of solve this or contribute to the solution. If we can split location from identity, that in itself already gets us some distance to this. Mobile anchor points, this is an issue in mobility. There's a lot of design in 3GPP, for instance, for anchor mobility. Kalyani will go into a lot of the more rationale, how to get to anchorless and the benefits of that. And the last one, low latency applications. So this is kind of under the assumption that as we go forward, AR, VR, new applications will come in. Low latency will become more and more of an issue in real networks. So we classify that as mobile. It's already kind of an assumption in data center networks.
Only clarifications, right?
Only, yeah. Just, can you relate the identity tied to location to MIP architectures? I'm just curious on that. I didn't quite understand that point.
Excuse me?
The identity tied to location? Is it
identity
tied to location? How is it? I'm
yes,
trying
it's
to relate.
in the address. So your identity and your and location are basically encoded in the address. So it's difficult to split those out, which basically means the address, the node has to be static and tied to that specific location. So this is one slide that just basically shows the process. If you're not familiar with ILA, it is what we're calling address transformation as opposed to NAT. I'll explain the difference there. But the idea is part of the IPv6 address is an externally visible prefix. And when we go to send that to a specific location, we do a transformation of the upper bits in the address to what's called a locator. Locator is something that's routable in the network to the actual location of the node we're talking to. So this, for instance, could be a host that has a VM that's running, which is our location, or the node we're talking to. Could be a device in the network where we need to route to an eNode B. So there's some concept here of that the node has a persistent identity and a location, and the upper bits in the address are used to express the location. So to transmit, we transform those upper bits to the locator, packets sent through the network. At a peer point, the reverse transformation is done. So the important thing here is that to the sender and the receiver of the packet, they do not know this is happening. It's transparent to them. So in that regard, it kind of has the place of encapsulation. It has the same functionality, or at least a similar functionality. So some of the properties of ILA. So as I mentioned, it is an identifier locator split protocol. So location and identity are kind of separate concepts in the addressing. It performs network transformation. It's not NAT on the basis that transformations are always paired. So unlike NAT, whatever you transform into a locator address will be reverse transformed to the original identifier address at some peer before it's received, the packet's received. It is completely contained within the network layer. There's no parts of this that affect the transport layer. It's completely agnostic to the transport protocol, so it can run with any of them. And it's transparent also to the endpoints of the network. And as I mentioned, it's also transparent to the network devices themselves in the sense that if I have a TCP packet that undergoes an ILA transformation, it still looks like a TCP packet. It just happens to have a different address. Any stateless mechanism in the network, ECMP, segment offloads, things like that, will not care that it's not actually the endpoint's address. So the scope of ILA, there's basically two main parts before we get into the use cases. So the data plane, this describes all of the protocol processing. It does not change the on-the-wire protocol. It is only changing or rewriting addresses. We do consider transport layer checksums. So when we modify the destination address, for instance, in a packet, that in theory invalidates a transport layer checksum that's doing a pseudo header checksum. We do want to keep the checksum correct at all times in order to satisfy, say, some intermediate device is actually checking the checksum. So there's a relatively easy mechanism. I think it was invented in a routing group. It's called checksum neutral. Simple idea, look it up, but it allows us to keep the checksum valid even after address transformation. Also, data plane has a different number of address encodings. When we started, we kind of assumed a 64-64 split, so 64-bit locator, 64-bit identifier, much like ILNP. Over time, we've kind of relaxed that to allow different encodings. The control plane, this has a lot to do with the mapping system. There's been discussion on mapping systems in various groups. The idea of the mapping system is basically it's a distributed database of identifier to locator mapping. So this is the thing that kind of the equivalent of a virtual to physical address mapping in NVO3. How do you find the location of the node that you're looking for? So the control plane, that can be managed by standalone protocols. For instance, there is a Lisp control plane that potentially could be used with ILA. Also, we want to leverage existing control planes. For instance, 3GPP has a lot of control plane that we would also like to use. So we want to be a little bit flexible on the control plane. So ILA does have some interesting limitations. So first of all, this is IPv6 only. We're not going to try to somehow shoehorn this in IPv4. It's probably not enough bits. It is important to realize that ILA is not extensible. And from that point of view, it's in a sense, it's anti-encapsulation. So whatever we can fit into the bits of the address in the transformation, that's as much information as we can put into ILA. So if you really need encryption or fancy authentication, a whole bunch of things, ILA may not be for those use cases. It is designed to be fast, efficient, and have minimal impact on the network and the host. Complexity of the data plane. So one of the side effects of it not being extensible, this may push back some more complexity in the control plane in order to keep the data plane kind of very simple. It does not naturally support multicast. This is something we could talk about as we go forward, how to integrate multicast. But most of the use cases initially, really unicast is the more compelling thing to look at right now. ICMP does need consideration. The problem here is if there's an ICMP error in the network that's generated after a transformation, what's going back to the host, the address in the packet data will have a locator address. That's kind of an issue because we want to keep the whole thing isolated. So there will need to be special considerations for ICMP in order to avoid that sort of leakage. So there are a number of considerations that have to be considered, and a lot of these have to do more with any sort of technique or scheme to build a large scalable mobile network. So scalability, security, privacy, DOSability, essentially the four pillars of a mapping system. So in terms of scalability, some things to consider: the number of mappings in the system. Right now, we have maybe 100 million nodes in some network. That could be 100 million. Obviously, we want this to scale. With IoT coming on board in the data center, we're going to be talking about giving more and more things, not just tasks, but objects, addresses. So the number of mappings will need to scale. In addition to the number of mappings, we have to consider the rate of mapping. So everything, if we assume everything is mobile, a lot of these things are going to be moving around. That's going to require changes to the mapping system database. What is that rate and how do we absorb that rate? Kind of related to both of those, the throughput of the data plane. Obviously, we expect throughputs to go up, packets per second. So that will have kind of feedback into how we structure at least the mapping system and the data plane. We consider the total state in the mapping system, how that's managed. So the protocols that you use to manage such state, those have to be scalable in themselves. And then one of the trickier things actually will be caches. And this is a little controversial because we know caches are inherently, in some sense, they can be DOSed and things like that. So there's obviously a lot of history with caches. So we do need special consideration. If we need a cache in order to scale, say, the number of mappings or to get the latency down, we will need considerations for that. I'm particularly concerned, for instance, in a public network, what are the DOSing, DOS mitigations on a cache system? So security aspects, mapping system contains personally identifiable information. Locators may contain geophysical locations, so they need to be hidden. Identity IP addresses could be mapped to devices, and devices, in the case of personal devices, mapped to users. So this becomes personally identifiable information. So the mapping system needs to be secure protocols. We need to limit the visibility of the data. I tend to think this kind of precludes having one gigantic global mapping database for the whole world. And of course, we need to consider law enforcement considerations. What are their requirements? That has to be part of the mapping system security considerations. Inter-domain solutions, this is obviously a whole nother ball of wax. When you consider what happens within domain, we can fairly control that. But if you want to have two domains speaking a protocol like this, the requirements of the security between them become very interesting. So those are considerations. I'm not saying that we necessarily have solutions or have to have all these solutions, but in the mapping system, these will come up in discussion. Privacy, as I mentioned, this can be viewed as, can we help privacy, like with Identifier, Locator, ILA? And I mentioned that I did talk about privacy and addressing on in an area on Tuesday, so you may want to look at that draft. Fundamentally, giving a /64 to a device, that prefix that you give that device becomes an identifier for that device. So there are security, potential privacy issues with that. Privacy quickly becomes a balance between scalability. So in a perfect world, if you want a perfect privacy, everybody would always use a different address for every flow. That's obviously a scaling issue. So there's going to be some interesting discussion and trade-offs potentially there. Locator privacy, as I mentioned, locator, say in a mobile network, may actually indicate physical location if that's like the locator refers to an node or something to that effect. So this is another tricky thing. How do we prevent locators from revealing identity to third parties? DOSability I mentioned, and so I think this is going to have a lot to do with the mapping cache. If we have a cache in a public network, it will be target of attack, especially if it's being driven by third-party activities. So this is one thing we need to do. My recommendation is to have quantitative explanations of why a DOS mitigation works, and hopefully that kind of narrows down some of the issues. So I will cover the virtualization of the data center use case. Kalyani will go a lot more into the mobile use case, which is kind of the primary focus for this exercise. But as I mentioned, for data center virtualization, the concept here is initially we wanted to have every task in the data center, every unit of execution have its own IP address. There were several reasons for that. One of those was we wanted seamless container migration, and that would allow it. But eventually, everything gets its own IP address. One of the critical things in that environment is if we introduce this concept, everything having its own address, that mechanism to do that has to really be performant. Applications really don't care if infrastructure is changing for infrastructure's benefit. So this is to give the network more malleability, but applications already running with a certain performance, they don't want to see a degradation. So ILA had that aspect from the beginning that in that model, performance has to be really tight. So we have a tight bound on performance expectations. Network virtualization is kind of similar. I did present ILA and NVO3 a couple of times. It does have some different aspects because of the performance, bounds may not be so tight, but there is aspects of tenant isolation. So we need ILA to make sure that it can convey tenant IDs within the addresses. There's also an interesting application in ILA using IPv4 to IPv6 address translation, where we can allow, say, VMs or tenants to contact common data center tasks without using NAT, which is kind of a benefit. So with that, I will turn it over to Kalyani, who will go into the mobile use case.
Actually, is it possible to get one clarification question in before you step away?
If it's a clarification, feel free, yes.
Yeah, it's just you did not go into identifier assignment, which presumably would be an issue at scale. So I was wondering if that aspect had been considered. How identifiers are assigned to either processes or end systems or whatever, because that's clearly they need to be unique. And that to me sounds like a large administrative problem that needs to be considered. That's why I'm asking.
Yeah, yes, it is. If you look at the ILA protocol draft in the appendix, we gave some mechanisms to do that. We actually implemented something clever in the data center. We actually use a combination of a timestamp and a registry number. The nice thing about IPv6 addresses, even if you split them into 64 bits, you still get a big chunk to work with. So the identifier fits into 64 bits. There's quite a bit of flexibility to do there. I'm hoping we don't have to do anything like duplicate address detection. However, you would get that in the mapping system kind of for free, but it is an issue.
Yeah. Okay. Thank you.
Clarifying question or comment. So I assume that you want interoperability with current IPv6, but you didn't explicitly say that. Right. One end can speak
Yes.
ILA, the other one speaks current IPv6.
Yes, but to the rest of the world, there shouldn't be any difference, right? So for instance, on the internet, somebody may actually have an address that's going to be transformed in a provider network, but they don't know it's still an IPv6 address.
Just a quick thing. I'm still having trouble here.
Okay, go right ahead. We're having a little display problem, so now's a great time to change the battery, Mike.
Okay, go ahead. See, this is PDF file, but I will just do this. Yeah. Okay, while Samita is trying to set up the PowerPoint or a PDF version, the mobility use case is the one that I will be describing. We have had a lot of conversations with several other operators as well. And I would like to thank my colleagues within Verizon who participate actively in 3GPP for explaining the 5G system architecture on the RAN side, on the services side, on the services-based architecture side, and the variants over there. And I also thank my transport side because this use of ILA for mobility management bridges two kinds of architectures here. One is the 3GPP mobile core overlay, as well as trying to tie it with the transport network that we have underneath that. So it was very important for us to go through all of those in order to see if this would work for us as a use case. What I'll cover is the use case and why ILA and how does the ILA fit into the 5G architecture. Anchorless mobility is a topic that constantly comes up, so I'll try and explain something and then maybe there is a recommendation for the way forward. The use case is really looking at the release 15 core architecture that 3GPP has specified. And this is using the services-based architecture. As you can see, the top part of the diagram shows the control plane functions, and the lower part of it shows the user plane functions. Mobility management is there on the radio side. The left side, you can see the radio access network and AMF. Those remain the same. The focus of where ILA would fit in is on the core network side, the mobility management in the core network. That is depicted by the session management function and the user plane function in the middle that is blocked over there. Why ILA? One of the reasons ILA is attractive is because it does not have any encapsulation and there is the promise of elimination of tunnels. And why is it important for us to not have encapsulation and tunneling is if the packet is a 15-byte IP packet, 50-byte overhead is not an issue, 3%, you can go ahead with that. But if the packet is a small packet size of 100 bytes, if you have an overhead of 50 bytes, that is significant. And if the overhead is reduced, what does it mean to us? It means that there will be a requirement of reduced backhaul capacity. And as we go into the 5G networks, the network densification is happening. And this means that we will have antennas covering smaller and smaller areas, very distributed into the areas. And we need to have backhaul capacity that gets us to the services and the control plane functions, as well as getting to the internet and other applications. So reduced backhaul capacity helps us in the 5G network in operations as well. The second reason for ILA is it promises anchorless mobility.
The current 5G architecture uses the anchor point in a way that makes it difficult for us to offload traffic locally to support edge applications where we are trying to get to the low latency applications. We will need to have a separate anchor point closer to the radio access network, or sometimes in the cell site, in order to meet something like the 1 millisecond latency. So having anchorless mobility helps in simplifying the network, and it also reduces the state information. And this goes to the third point. When we have no encapsulation, if 1 millisecond is a requirement, on the radio access side, they are trying to get rid of many microseconds and so on and so forth. But once we hit the packet side, we are having so many other network functions and conversions and encapsulations, which does not help in the low latency application. So this reduced packet processing and no additional network functions comes by the fact that ILA can be provided in the Linux kernel. And if we do it right, the E node B or G node B can be implemented on that, and that would help us get rid of some network functions at the edge. This is the protocol stack diagram from 3GPP. The bottom right shows how the encapsulation works. There is the GTP and all that stuff. What ILA promises is that you can remove the encapsulation. The backhaul that I mentioned in the previous slide is the N3 interface over there. And the anchor point part comes into picture when you see the two UPFs in the diagram. When you have to offload locally, the second UPF is placed alongside the access network. And you will also need to support some anchor point over there in order to support mobility. Then here is a proposed architecture that we are targeting for release 16. We took the 3GPP services-based architecture. What we show here is the ILA mapping system, ILA node, and ILAR are connected to the services-based architecture. And the rest of the system remains the same. And what the proposal here is to have ILA as a network slice for some of the applications that do need the reduced, do need the high performance benefits. The ILA can be used. If there are things that need to go back to the GTP-based slice, we can do that. So the premise is ILA would be used as a slice in the whole system, and the gold-plated GTP-based high-reliable system can continue to be used for voice over IMS, for roaming, and things like that. The proposal here is to have the control plane interactions using RESTful APIs. 3GPP has done a lot of work, or is continuing to do a lot of work in defining the services-based architecture for all the network functions that are defined there. And the ILA node and ILAR and ILAM, the proposal is to do it in the same format as that. And this architecture allows flexible implementation and deployment options, which means the SMF and ILAM could possibly be implemented alongside the SMF, ILAN, and ILAR could be implemented together, and so on and so forth. And so we'll reuse a lot of what is used in the networks today. Roaming.
One quick clarifying question. So in this, the way you're using ILA in this mode, Kalyan, you're not removing the anchor, right? ILAR is still your anchor point, correct?
No, I'll get to that in the next slide.
Okay. Just one other clarification from the previous slide where you showed the stacks.
Yeah.
In the PDU layer, is there an IP header?
The PDU as defined in 3GPP can be an IP packet, it can be an Ethernet packet, or it could be an unstructured packet.
So this is IP in ILA for a normal IPv4 or IPv6 PDU session?
Yeah.
IPv6 only. It's IPv6.
No, it's IP in ILA.
The IP packet
IPv6.
could be anything. The
So
payload could be anything.
So when they say they are dispensing with the encapsulation, what is being dispensed with is UDP and GTPU, to be clear.
No, the payload will be, so it would be put into the IP layer that would then be transformed as the UPF. So it's not.
Doesn't the packet have to start with an IPv6 address so you can transform it?
Yes.
So it's got to be an IPv6 packet. The whole
So-
the user
so-
packet is an IPv6 packet. They're dispensing with the UDP and GTP overhead above the IPv6 packet. No, there is no substrate here. Otherwise,
Okay.
we'd be encapsulating, and Tom doesn't want encapsulation.
Okay, so this is why I wanted to put ILA in parentheses here. It's not actually a layer. It is, in this picture, I guess the PDU would actually be the IP header from the user. That's what we're modifying. So when, say we're sending a packet to the end host, it comes into the network as an IPv6 packet. We modify the destination address, traverses the network at a point close to the end host, it gets reverse transformed.
Okay.
There is no encapsulation at all.
So UEs originate SIR prefixes.
Yes, but they don't know that. All they know is they have an IP address.
Okay.
The IP addresses assigned to UEs use SIR prefixes. It's probably a better way of putting that.
It's just
Yes.
an IP address as far as they know. And we do want a mode where we can do a /64 assignment also. If you're wondering.
Okay, so that cleared that up for me. Thank you very much.
Hi, Rashmit here. So one question is that given that we will have always, at the beginning at least, a mixture of IPv4 and IPv6 mix at the beginning, is there any interworking plan in the ILA?
No, there is no interworking plan because we will use it on a slice that supports IPv4.
Okay, so that's what
we'll do.
okay.
Yes.
Good. Thank you.
My name is Margaret Collin from Painless Security. I used to be Margaret Wasserman. I actually wrote the NPT v6 draft with Fred Baker that uses the same checksum neutral mapping. I think originated it. The issue, I have a question, but I'm not positive if it's for you or the previous presenter, but it came up in looking on this slide. I know it's checksum neutral, and that's great. One of the things I'm not understanding is I know you passed the ILAMP stuff so that the other side knows how to map it back to the same address. What happens in the case of dynamic routing or asynchronous communication, and how does it handle using this, getting the same address?
I have a slide that shows you from the network perspective. Give me 1 second. I'll go to that slide. Let me finish this one. I'll go to the next slide. And
Is it on the next slide?
Yeah,
Okay.
yeah.
All right. Thank you.
Okay, so what I have in the bottom part of the slide is that for roaming, we can reuse the 3GPP principles because this is no different than whatever the services-based architecture shows. However, there will be some topology hiding things and other kinds of aspects. 3GPP has worked with multiple mobility management protocols in the past, PMIP and GTP and so on and so forth. This is no different. If one operator supports one mobility protocol and the other one supports anything, the common one will still be GTP. And so those kinds of principles can be reused. Security and privacy, today's mobile operator network, we have the same kind of issues that we have addressed, and those principles will be reused here. Regarding scalability, mapping, and control plane signaling, again, the network design aspects from the 4G networks will be used. If we have to deal with trying to redirect the packet to another location because the UE moved, there are principles in the MME to the E node B, how that takes care of. There is an X2 interface. Similarly, SGW to E node B, we will try to use the same principles for the ILA nodes that will be used closer to the radio access network. And here is the slide that talks that I'm trying to depict the anchorless mobility. But it also tells you how the operator network is designed. So on the left side, you see the radio access network, and that's where you have all the air interface. But then you convert it into the IP packet, and then you try to get it to the other side onto the internet. So this one is a very managed domain. On the right side, between the internet and the mobile core, we do have the traditional IP MPLS network in there. So we have the P routers, PE routers, and the choke routers, everything in there. So the ILAR will be behind that one. And what we have on the radio access side, in the past, we could not see the IP packet till we hit the point where we are connecting to the internet. So it is a tunneled one. But in the low latency cases, if you want to break it out, we had to bring the current architecture suggests that we bring the gateway down to the E node B, a scaled down version. But this one allows us to see the native IP packet as soon as we get it out of the radio access network. So I tried to show one of the flow. The top flow is showing when you go into the internet, a UE requests something from the internet. When the response comes back, the packet has to go to the place where the UE is. So it looks up the mapping table in the ILAR, and then it directs it to the place where the packet UE is located. The second one is UE to UE communication, and that one uses the caching in the ILA nodes. You don't have to go back to the ILAR, the anchor point, and then come back in. So the ILARs will really be located at our peering points, and that's how it will work. So I do not know if it answers.
So if I understand correctly, you do the transform at one edge,
Yes.
and then if it hits another transformer at the other edge, that one will have been informed of the
Yes, so
mapping.
it is a contained one. So
But it's conceivable that there's traffic out on the internet that doesn't hit another transformer, and that's just effectively natted then at that.
I believe, Margaret,
Yeah.
I think there's an issue there worth exploring, but I wouldn't call that a clarification. I want to let her get through one
Okay,
more
I'm just trying to
slide.
understand
One
how
more
it
slide,
works,
yes.
which I thought was a clarification, but okay. I mean, I've read all
We're
the
not-
drafts and I don't understand.
I have
so-
hypotheses, but it's a fair question, but I need to let her get through, and we're running out of time, Kadyani. We need to move to your last
well,
slide.
I'm on the last slide now. So what we would like to do is our focus is mobility use case. So we would suggest that the ILA specifications, even though there are 3 use cases, that the specifications be done in a phased approach, focus on the mobility use case, and the deliverables that would have to be done is do the ILA core protocol, and we need some reference control plane protocol that can be used to develop the APIs necessary to connect to the services-based architecture, and the architecture considerations for the mobility use case, like what we talked about here.
So switch to the, okay, do you have a clarifying question on this material?
Yeah.
Your name first. And then
Yeah, 春山雄from Huawei. For your proposed solution can just solve the issue of the mobility issue in the 5G, but but for another issue is not considered for the QoS enforcements. Now in the 5G we use the QFI ID in each GTPU header to identify which QoS flow this packet belongs to. In such case, the runs and the anchor can decide how to do the QoS enforcement.
Yeah, so
But
that's
not-
why we are
no.
suggesting a sliced architecture. This is not a replacement of GTP for the whole architecture.
Yeah, I
So
know.
for specific applications, specific needs, that is the slice that we
Yeah,
will
I
use
know.
for.
So in such, if such solution is used, then maybe only default QoS or some default QoS used. If we need some enhanced different QoS for different IP flow, then this solution maybe need more consideration and study.
Okay. Now bring up the question slide. So we have tried to prepare some questions to shape the discussion here on what do we need. And as soon as Samita can get those up for us, thank you very much. Yeah. There. So the discussion at this point, and Tom and Kalyani are staying available because they really can answer most of the questions better if you don't understand these. But the things I will try at the very end to find out from folks is, do you understand the problem space they're trying to address? If not, ask questions about that. Do you understand the intended scope? If not, ask questions about that. Are there issues that you think any further work on this will need to address? If so, bring those up so we get them minuted so we can keep those in mind as we explore how do we want to take it forward. And similarly, did you understand the use cases? If not, ask about that. Okay, and looks like we have one from the Jabber, so
Yes.
Evangelos, start with that.
JavaScript, Eric Klein asks, how does this suppose UEs getting /64s allocated to them?
The supported UEs.
Yes.
Select 64 allocation. That's a very good question. So remember the part where I said that we had to relax on the canonical 64-64 split? The solution for Slack 64 assignment is to use an encoding in the upper 64 bits that both encodes a locator and identifier. There's a level of indirection at the locator node that we have that is described in the ILA protocol draft, I believe. Excuse me?
So the question from the room was, how much does that cost?
How many bits? I forget the exact encoding, but the idea was the identifier is not global. It really is an index in a locator specific table. So depending on how many users you need, say in that particular enode, that would have to do with the size of that table. So I think we wanted 20 bits for that, plus some number of bits for the network prefix. It seems to work out. So to take a look at the draft, I don't remember the specifics, but there is an algorithm described there.
Okay, next.
Okay, Dave Allen Erickson. I guess the key concern I would have is I understand some of the problems ILA is designed to solve, but I have not seen an elucidation of the full set of requirements for each of the use cases it is proposed to address. And until I see that and can understand that mapping, then I'm not prepared to say that I fully understand the problem space that ILA is intended to address in all of the applications it's proposed to address.
Okay,
So
AD,
I would-
you want to comment?
Yeah, Suresh Krishnan. So AD override. So the thing is to see if these problems are real and there's like a community willing to solve the problem, right? Like ILA may or may not fit as a solution. Like we don't know that. So let's do the first step. This is not a working group forming BOF, just to see like, if people agree there's a problem like worth solving, and then the proponents can go and work at another pass at this.
Okay,
But the thing is, if we're going to take on this as a solution that would fit into a 5G slicing framework, is expected to support the business of mobile broadband, et cetera, there's actually a long list of things I have not seen. And that does concern me. And I would like to see that before I want to rush off and do this. So
fair enough. Next person, please. State your name, please.
Mason Ledai from University of Essex. I kind of understand the use cases you are trying to address. I'm not sure how you're going to do that if you don't support multicast and you don't know how to do any cast.
Well, so it's not that we don't support multicast, it's that we haven't fully spec'd it out. There is an encoding that does support multicast.
Right.
So it could be support. But as Kalyani said, it's like also saying we don't support IPv4, but yeah, that can still exist in the same network.
Right.
So I think that would go under the requirements for that specific use case.
Right. Okay.
So what are the requirements for that use case? And it also depends on whether you have to support multicast in this exact mode. So you could also say, well, you're using native multicast anyway, that already works. So how do you deal with multicast? So it may actually be a slightly different problem that's being targeted too. But I do agree, as a whole solution, yes, we have to consider multicast. So my statement was, native multicast is interesting because it's the source address that routes the packet. And here, for identifier locator, we're changing the destination. We would have to think if it makes sense to actually transform source addresses.
Yeah.
My feeling is that's a lot of complexity, but that would be something to look at
So is
to
that
how
like
it deal with
a
that.
work in progress, future work? You do appreciate obviously the importance of it.
Yes.
Okay.
Yeah.
And is that the same for any cast? Because you are saying that caching is not as straightforward. It's a bit tricky.
So Anycast is a little bit different because I think, in a sense, this does support Anycast because
I would
you're
have thought
directing
so.
the packet to the specific node. So from that point of view, it actually is pretty good at Anycast. I can do the mapping, and then instead of doing encapsulation to get it to an Anycast node, I can just do ILA, and that's like no encapsulation overhead. So from that point of view, it actually work well. And I believe that's one of the use cases that Facebook is actually deploying right now is Anycast with ILA.
Tom, given the length of the line, make your answers shorter.
Lorenzo Culidi, let's see. I think the problem space is kind of varied. I think ILA is a great fit in the data center, but there's a lot of things that are being proposed here. So I guess I'm really unclear about the scope. I don't know, because there's a lot of problems that intend to be solved. Also, can you go back to the slide where we talked to the internet?
No, unfortunately, we cannot easily go back to the other slides.
All right, but that slide doesn't work. All right, there's like basically insoluble scaling problems. We've had conversations on the 5-gang IP list, and my assessment is that it's three orders of magnitude away from the technology that we have today in terms of memory bandwidth in routers and forwarding table size. So if that's the use case, I think Kalyani is proposing that we start with that use case, but I don't think it can actually be made to work. And so that's sort of an important consideration.
Okay, I had conversations with my transport colleague. He's actually sitting over there, and we talked about it. So we do have I understand what you're saying for the facing to the internet kind of a thing. So there are the routers that are over there that deal with that. This one is towards the access network side. And we do not have the per user kind of router advertisement going over there. And then there are also the new kind of routers where you can go to tables that are 80 million and so on and so forth, even if you get to that.
Let me paraphrase his concern. I don't believe the documents have described a workable way. It may well be possible to make it work, but at the very least, I don't think the documents have captured a workable way. And it's important for taking things forward that people actually be able to look at common descriptions.
That's a subset of my concerns. Yes, I would challenge anyone to make it work. But yes, the documents, it is a fact that the documents do not describe how to make this work. Yes. But it's important, before we decide to say we're going to start with this and make this the primary use case, like I said, I personally don't think we can make it work.
This is Dino. Is interworking part of the BOF questions? Is that in scope?
Interworking of what with what?
A host that originates a SIR prefix talks to a regular IPv6 host. Is that in scope? I'll sit down if it's not.
I think it has to be.
Okay, so that means I can ask this question. Okay, question for Tom. If a SIR prefix is a source in a packet and a destination is not, and the packet goes all the way to an IPv6 host, when it returns, it's going to come back to the locator address and the destination. How does the ILA node know to translate the destination address to the SIR prefix and not the source?
Because in that unicast model, it's only ever translating the destination. On the outbound path, the source address is not touched.
The source on the outbound path, the source address is
so
touched
the SIR address
because
is
it's
just there.
no, you're not understanding. On the outbound path, it is translated because it's a SIR prefix, and you know if it's a SIR prefix, it must be translated. The destination is not.
But it's in the source address on the outbound path. You said.
I think there's a lack of clarity on whether the source or the dest is being translated, and in different directions, you need different translations.
Right,
consider just the destination is transformed in this model.
I know that's the only one that needs to be transformed, but how do you know that? You have to keep state.
Well, because the destination is clear in the packet. Okay, we can talk offline on that one.
Yeah, I think, again, it's something, I think that one, actually, you guys have an answer that's clear, but it's hard to extract it.
Okay, next question. Okay.
Daniel Huang, ZTE. And actually, I understand the problem and the scope and the issues the IOA is designed to address. Is my understanding is in pretty much the same scope of ICM. So my question is, what the exact difference between ILA and ICM?
Between ILA and what? I couldn't.
ICM, Information-Centric Network.
ICM works at HTTP header level. That's very different. Let's move on to the next question. I really, that's very different. We won't debate what problems they solve. Remember, we said at the beginning, we're not comparing with other solutions.
Hi, Tony Lee, Arista Networks. So what you're trying to do here is to change the fundamental architecture of the host. And yet you're not changing the fundamental architecture of the network. What are you going to end up doing is you're going to end up with a mismatch. And you're starting to see that already because of ICMP. This is a clear thing, a clear indication that you have a architectural problem. Why not just bite the bullet and make an architectural change so that this is a first-class element in the architecture?
So, but I guess the question is, what is the architectural problem, right? So if you consider the 5G use case, and I think Kalyani articulated that, the architecture architecture problem is, say, we want anchorless mobility. How do you solve that problem? And that's where
allowed to
the
talk about other
architecture
solutions.
answer starts to come. And I can also mention, so if you look at the data center use case, it was pretty clear. The architecture is for mobility was fundamentally pretty simple. We need to know where someone is, and we know how to get the packets to them as quickly as possible, and they can move around. So in the mobile use case in the data center, it was very clear, and I think there's a lot of analogs in the mobile use case. So what we don't want to do, it would be nice if we didn't have to change the architecture completely, but we do want to evolve it at least to handle, as I said, seamless mobility, highly efficient, get those low latency applications.
Well, that would be fine, but remember that what you're doing is really more fundamental than just dealing with the 5G problem, right? You're trying to deal with multi-homing, all mobility, regardless of media. You're trying to truly separate the locator from the address throughout the stack.
Well, I mean, throughout the stack is kind of limited, right? This is a network layer protocol. It also can be incrementally implemented. And I would argue it's actually simpler than, say, we wanted to introduce a new encapsulation, because there's a lot fewer moving parts to it, right?
And we're not comparing alternatives. But Tony, okay, let's move quickly, because I do want to have a few minutes to take a hum of what people understood, at least in the room. I'm not expecting resolution, but I do want to let the three people on the line ask. And yeah, my IAB shepherd gets to tail it.
I think I do understand both the general problem space and the two use cases that you're well, I can't say I understand everything about the 5G one, but I think I understand the two use cases that you're talking about. And I think I understand what your intended scope is, ish. One of the things I'm unclear on is pictures where this goes out on the internet. I think you're going to run into problems. I started to write a very similar draft in 2008. It's called Draft Wasserman Ram Trip. And that draft used the same mechanism, and it tried to solve this problem, but I ran into intractable problems that I don't see that you solve. One of them was ICMP. One of them was what happens when you have dynamic routing. The other was around nodes out there that don't have a translator and how they perceive. One of the problems is that you don't have the zones you say you have in your draft. You don't have, we're in identity space zone and we're in global zone. We're in identity space for my addresses and global for everyone else, all global, and identity space for somebody else's addresses and global for everyone else, including the other end of the connection. And that has some ramifications that aren't really captured in your drafts. And I would love to work with you on this if there's a decision for it to go forward. I'm not trying to kill it, but
question about how to make sure you're hitting a transformer. The locator itself is an address of a node. So when the packet has to route to that node, it can't route anywhere else, because you're overriding that with basically a prefix that says that's the node. ICMP.
Well, then you have a problem with how do you find a transformer, right? I mean, which is a different problem.
So that's the mapping system. I acknowledge the ICMP problem. The ICMP is going to be tricky in any state. I mean, imagine, so we know tunneling has the same sort of issues. Segment routing has issues with ICMP. ICMP is a pain. And your third thing was about identifier spaces. Yes. And that kind of goes back to my statement. I don't believe in the global identifier space. I think identifiers are going to be fairly localized, which makes this more like an optimization within a single network. I think there may be opportunities to make inter-network things, but let's assume for the beginning that's going to be contained in an administrative domain, one identifier space, which is indicated by the upper, like the SIR prefix, which is the externally visible prefix.
Yeah, and unless you control the whole thing, like in the data center case, you have to get into the issue of what if this gets mapped again? And that, I think, is not entirely well understood.
We have some options there.
Hi, I actually have a couple of questions. So I do. Hi, I'm Padma Huawei. One, I do understand the problem space because we've discussed this at length, and I do see the intended scope. I do have a couple of clarifications. You discussed about privacy, which was a big topic a few months ago on the mapping system. I do see you put identity, and this was a big discussion. So I'd like to understand, one of the questions was about long-lived identity. And here, it looks to me that the solutions proposed before on actually having the identity obfuscating the real identifier, is this what you're doing, or is this something different?
So identity is always a little ambiguous to me, but let me say that we have identifiers which identify something. We can give multiple identifiers to a node, and to the outside world, if they see, say, two addresses with two different identifiers, they should never be able to tell those refer to the same node. So identity, if identity expresses the who, it cannot, specifically the who, like that device. My claim is it cannot be in an externally visible address. For privacy, you need to obfuscate that somehow. And I think that is where ideas and things like that get into.
Yes,
so I'll accept
exactly.
that
So
as a
I wanted to
clarification.
make sure that we are on the same page, because I think I'm happy to see that, because I think now there's a real understanding that identity is needed for privacy, or else it's very difficult to achieve privacy, especially if you're keeping your IP address as one fixed. Everybody who look up this. So that would be one. And the second thing I wanted to ask was, I see that you're actually having a lot of similar requirements that we actually put in ideas. Can you confirm that or not? On the requirements of the mapping system?
I would say the mapping system, if you notice, it's almost orthogonal because it is a generic thing potentially for many identifier locator kind of split protocols.
Again, I don't want to go into that too much. That starts getting into comparing with other work, and we don't have time today. We're already over time.
Okay.
Yeah, we're not comparing. I just want to know.
Okay, we can take it offline, but I generally agree there are similarities.
A quick question, Sri Gundavali. So tunnel removal is one of the key objectives here, right? And I assume you want to achieve that with the approach of transformations, address transformations, right? So now today, if you look at GTPU or GRE, in that we carry a number of fields, right? Essentially, you have the GRE key, right? And now within this 128-bit space, you need to put the identifier, you need to put the locator, you need to put the cost. If you want to do cost preservation, you need to do the DSC. Will we be able to encode everything within that 128 bits? No, actually, you don't even have the 128 bits because your provider is given only a part of the block, right?
For the mobility use case, we are looking at it as a managed domain within an operator network. And it's some cases, there may be some hops in there, but most of the time it is like trying to get everything from the antenna or the radios to one of the centers where we can make it convert it into the packets. So we are not taking everything that has to have all the advanced features that a GTPU or even what somebody else was mentioning before. This is for a particular slice that is simple enough that we can put some IoT traffic or where we do not need all those advanced features in there.
So most of those features will not be supported or cannot be supported.
Yes, that's the under slice.
Eric Nordmark, just a quick comment. I don't think we need to respond to this, but just want to make sure it's on the list of things to consider is, if you care about doing ingress filtering inside the network, maybe you need to some additional awareness that we have these SIRs as well as regular prefixes. So it's something to add to the list to go look at.
So you're referring to, we have filtering within the network that has to be prepared to handle both types of addresses?
Yeah, ingress filtering in particular.
That would be a consideration.
Okay. We're now going to, Suresh, I was going to take the hums and then let you have the final word. These are going to have to be quick. I would like a hum of those people who think they understood the problem space that was described. A goodly number of hums. Those people who think they did not, feel they did not, it's not a question of thinking. If you didn't understand the problem space, please hum. Wonderful, thank you. Okay, did people understand the scoping that was laid out? Please hum if you did understand the scoping. Not as many. Please hum if you didn't understand the scoping. Unnoticeable hum. I'm restating this so that Uma can get these in the minutes. We've dealt with other issues that need to be addressed. I'm not going to go into the use cases. Suresh, you get the final word.
Okay, Suresh Krishnan, responsibility. So the idea was to like get the proponents to understand like the scope of things they need to do in case they come back here with like a better proposal. And I would really encourage people here to sign up on the mailing list and send any concerns that you have, because I know you have a lot of concerns. Looking at like the questions that came in, there's like still people who have issues understanding like how this is going to work. So please send the comments on the list, because the proponents requested like an hour for a BOF, and I granted the hour, but maybe we can certainly use more time, but we don't have the time today. So send everything on the list and we can flush it out and get the things out, because like the proponents really would like the feedback and they're willing to work, make this better. So, and then we can actually have a discussion on like whether we want to solve this issue. But like, I was like really happy to hear like a positive hum for the first one. So that's like a big step in this direction. So please contribute on list. Like the email list is ILA@IETF.org. So it's not like difficult to remember. So just sign up and send comments in. Thank you. Thanks for staying extra. Thank
And
you.
I need the other blue sheet back. Okay, wonderful. Can you take care of delivering the blue sheets? Thank you.